good afternoon. We are starting our fall new faculty research seminar series. We've done this now for past several years, and it's our pleasure to have our first seminar today being presented by Dr. Tarek Elfouly from Electrical and Computer Engineering Department. He is an associate professor there that joined us this fall. My name is Vahid Mutawalli, and I'm Associate Dean for Research and Innovation here in the college. So we started, I think, in 2014 doing these seminar series. So I'm going to share my screen here, and this is a sort of flyer. You can see today's seminar titled The Structural Health Monitoring Using Wireless Sensor Networks by Dr. Elfouly. And we'll have a total of 6 seminars. Next Tuesday, Dr. Rory Roberts, Dr. Noe on November 5, and Dr. Sargolzai on November 10, followed by last 2 seminars, November 16 by Dr. Tester and November 17 by Dr. Van Nest. They're representing several departments and also the Center for Energy Systems Research. Now, Dr. Elfouly comes to us with a great deal of experience. He has taught at Ain al-Shams University in Egypt as well as Qatar University before he came here. He's also had some industry experience. And his master's and Ph.D. degrees are from Besançon University in France. He has 3 US patents relevant to this area, and he has worked in area of wireless sensor networks and computer network research for over 12 years. He has a multitude of publications, and he has been involved in a number of interesting projects as well as different type of work over the years. The one that interests me most, of course, is the World Cup 2022, 2 years from now. Being a fan of World Cup football or soccer, and so maybe I'm not sure if he'll cover any of that today in his talk, but certainly we'd like to hear about that at some point. So with that introduction, I'm going to turn it over to Dr. Elfouly to start his presentation. He will share his screen, and once he's done, we will have a few minutes to have questions and answers. So at that time, you can either raise your hand or turn on your video, and that way we'll know you want to ask a question. Dr. Elfouly?
Okay. Thank you very much, Dr. Mutawalli, and thank you for this excellent introduction. I will be presenting about the structural health monitoring, and actually the motivation behind it was the World Cup preparation. So let me share first the screen. So, as I said, thank you very much, Dr. Mutawalli, for this introduction. As the motivation for this was the World Cup, because when we wanted to do some monitoring for structure, our focus was actually at the beginning on the stadiums. And we wanted to see if there will be an effect on the integrity of the stadium in case of having a big number of spectators in the stadium, especially that Qatar is new for this, and they didn't have that size of big event in the past. So we wanted really to have a system that can monitor this. So the motivation behind it was the World Cup. So let me start here by first introducing some of the research that I worked on. Okay. So mainly the research that we had and I had in the past, it was related to networks, related to some physical layer security. We as a group there, we had the opportunity to get funding, especially with the introduction of the new program at Qatar Foundation, which is called the National Priority Research Program. We had the opportunity to get funding for more than one project related to wireless communication, related to RFIDs, related to structure health monitoring. These ones actually I have are the latest one that was until 2022. Unfortunately, leaving Qatar University, I had to actually abandon this project. They didn't accept that I can continue it while I'm outside. For the other three, we already, the other two, we already finished them, so it was fine. We had also 3 other projects that are related to wireless communication and wireless networks. The one that is mainly on the topic that I'm talking today is this one. And this one, when we obtained it, was in 2013. As can be seen, it's after having the announcement of the World Cup. So it was actually, the motivation was for this. So we have, as you said, we have 3 patents. The 3 patents are registered here in the US, and they are all related to wireless communication, wireless networks. So let me start now about the topic that I want to talk about today, structural health monitoring. It's not a new field. A lot of people already working on structural health monitoring, perhaps many decades ago. So it's not a new field. But as a field, it has a very simple definition, that it's the process of implementing a damage detection and characterization strategy for engineering structure. So what was new is the work of electrical engineers in the last 2 decades trying to find the system that can detect these structure damages or structure degradation in the health of the structure. Before this, it was mainly civil engineers, and they are really trying to find ways to detect this type of monitoring or this type of health monitoring. So, as I said, the motivation behind it was detecting and localizing the damage. Of course, localizing the damage is perhaps more challenging than detecting the damage, and it depends on a lot of factors, especially the type of structure we are going to monitor. So if we are going to monitor a stadium, it's different than monitoring a bridge, it's different than monitoring a building, for example, a residential building or a business building. So we wanted to find some ways for monitoring the health of the building, and at the same time, we are trying to find some methods that take in consideration the new technologies that are introduced year after year. So we found that there are 3 challenges that will face anyone that wants to work on structural health monitoring with wireless sensor network. The first is the sensor node needs to detect signals as small as 500 micro G, which is actually it's not that easy. I think especially people in mechanical will know that we have really to have certain methods to detect this small value. The second is the source of distortion that is available is really high. Specifically, if we want to have these type of readings with an accurate, with an accuracy, a high accuracy, it's not easy because it depends on a lot of factors. When we are using our boards are all digital boards. So we have actually to convert from the analog readings of the sensors to the digital format so that our boards, our microcontroller boards can actually understand it. And because of this, there is an error in this. There is a digitalization error. There is some errors due to installation. There is some errors due to the environment where the sensors are located. So it was an issue actually. The second is the high sampling frequency. And this is also a problem, not only for the frequency that we assemble, we want and we need a lot of data, but it's because of the transmission of this data to the either the base station or to the server which is going to process the data. And the problem is that these sensors are placed in locations. Sometimes there is no source of power that can make these sensors work all of the time. There isn't. Sometimes a structure like a bridge could be in the middle of nowhere. There is a bridge, and you need to monitor the health of this bridge. So most of the systems that try to accommodate this, they try to use either solar energy, which is sometimes a problem because of the maintenance cost for the solar panels. But we try to see if we can find another way of generating or harvesting energy from the environment. The third challenge is the time synchronization. The problem is that most of the structures cannot be monitored by only one sensor. So we have to place many sensors on the structure. Sometimes there are hundreds of sensors, actually, if the structure is a big structure. So the problem is that there is a synchronization error between the different sensors we are using on the structure. And we have to, if we want to get an accurate result and to have a data that is reliable, we have really to minimize or eliminate this synchronization time, our time synchronization. So the aim of the research I'll present today is to try to present 4 points. First, developing an improved method for damage localization, identification, and detection. And actually, we had help from mechanical engineering department in NGIT working on this. The second was optimal design of the wireless sensor network for the structural health monitoring. And actually, this was mostly done with the research team that I was supervising with Ph.D. students, master students. The third point is analyzing and improving the reliability of the SHM monitoring. How can we make it more reliable through minimizing the time synchronization error, trying to make it reliable by harvesting energy so it will not the battery will not deplete very fast, trying to optimize the energy that we consume. So there was many issues we tried to study here. The last point was a project that we are currently trying to work on, which we try to diagnose the damage, which means that sometimes we don't know if there is a damage or no. We didn't actually, this building has not been, or we got some values for this building, but it's not being monitored all of the time. So it's being monitored at certain times and then we don't monitor it. So how can we, after a certain event, how can we detect if a damage happened or no? After, for example, an earthquake, hurricane, or something like this. But something to note here before going going further in the presentation, that most of the work we did was based on concrete. So the testing was on concrete. We didn't really try on wood because it's not very common to have wooden buildings in Qatar. So all the bridges are all concrete, the buildings are all concrete, and of course the stadiums are all concrete. So it was all on concrete. So the first point we are going to talk about is that developing an improved method for damage localization, identification, and detection. So what we did is that we had 4 different points to work on. First, we want to have a performance evaluation of experimental damage detection in the structural health monitoring. So what we did is that we went to the lab, we tried some structures, mini structures that we have developed in the lab under of course supervision from the civil engineering department, because we had to make it the same ratios. So if we have a concrete, for example, a column in a building or a span in a bridge, we wanted to have the iron or the enforcement that is inside it not to be, of course, the same diameter like the ones in the bridges or in the buildings, but to have them up to a certain ratio. So actually it was being calculated, and we did them, I think it was 2 millimeter, the diameter, or 3 millimeters, something like this. So it was actually done in a very well-studied way. And the second point is to have a damage detection and sustainability, study it, developing a finite element model to evaluate damage detection bridges in SHM. And this part, I will not go in a lot of details because this part was done at NGIT, but it was done in a very special software on a model that we developed in Qatar for a bridge that is a real bridge in Qatar. We got all the designs and we tested it. And we went and tested on one of the bridges, that small bridge that is inside the university, and we installed all of the sensors on this bridge to test it. And I will show you some photos for this. So what did we do? There are more than one method to evaluate the damage and to see the structure, to actually study the structure health. One of them is the mode shapes. And we have been told by the civil engineer specialists that were working with us that mode shapes give very good prediction of the study of the health of the building. It's more difficult to calculate, and it has to be calculated at the beginning of the design. So to test the bridge, or to test a stadium or a building, these mode shapes has to be actually developed or calculated at the beginning. But there is a way to calculate these mode shapes after this, using placing the sensors at certain locations on the structure. So the location of the sensors had to be fixed. So this is one of the models we had in our lab. And you can see here that we actually had the model developed on the software, which is called Lucis. I think it was the civil engineer did this in NGIT, New Jersey Institute of Technology. His name is Muhammad Mahgoub. As you can see, we had a master student working with him on this also, and we developed this beam, or this part of the bridge, and we placed the sensor on it. And what you see in front of you is a shaking table, and we placed these sensors on the bridge, on the shaking table, and we generated a certain movement that actually is emulating the movements of the mode shapes. It should generate the mode shapes. And we tried it, and then we did some damage to these structures. So we tried to make some damage, calculated damage also. So we put some damage at the intersections, and we tried. So we developed more than one, actually. We built more than one of these, and we tested all of them. So this is the shaking table. These are the readings, the acceleration using accelerometer, and we tested all of this in the lab. We did some damages at certain points in the structure, and we found that we can generate the mode shapes actually. This is the sensor that after here, it was not the same sensors that we are using. After detecting that this is possible, we actually built a board. This board using the Raspberry Pi that you can see at the left, and we installed on it 3 sensors. So we connect 3 sensors to this board at the same time. So this was the purpose this was the source of the motivation behind studying the time synchronization error also, because we detected that there is a synchronization error between reading the values of these 3 sensors at the same time. So why did we have 3 sensors at the same time? because when we placed them on the bridge, we wanted to see from all of the sides of the bridge. So you see here, this is the board. We had one sensor at the left, one sensor to the right, and actually we have these were two, but only we connected, we took values from one and then we tested with two, so we had four. But the board, when we had four, we had a problem because of the sampling. So we actually disconnected one. Okay, so because we cannot sample from the four, getting the number of samples required to get the frequency. So anyhow, this was the test that we did, and it was a real test, an experimental damage detection. And of course, there was no damage. We didn't damage the bridge. But what we try to do is we try to take readings from all over the day. So this bridge is used by students to pass from one side of the campus to another side. And it's not a very short bridge, but at the same time, it's heavily used during certain durations in the day. And we try to install this during some days, and we try to get the readings during these times and to see what is the effect of moving students all over the bridge. The second thing we did is that we took the design of this bridge. This bridge is a new bridge that was being developed in Qatar. It's called Arayan. And this bridge was, we got approval from the authorities to actually test with this bridge. So they gave us the design and everything. So you can see this is part of the design we used. And it was a very interesting project actually to test on a real bridge. But as you know, what happened, we did the designs, as you can see, all of the geometry, everything has been done, even the board with the box and everything. And after finishing all of the work, you see here, we even published some work about this. The authorities came and said that the project now, they are building you see a metro system or the subway. There is a subway that is going to pass under the bridge. So the company that is actually taking the project of the subway is going to install their own equipment on the bridge to detect if anything or any damage happened to the bridge. So we couldn't actually test on the bridge. We did all of the work that was required for it, and it was nice, but we couldn't test on the bridge at the end. The second point of my presentation, I'll try to go a little bit faster, so is the optimal design of wireless sensor network for structural health monitoring. So what we will do here, you can see all of these points. These are points that we worked on, and we even published in these topics. So in a summary, what we try to do is we try to see a multi-objective problem. We try to solve a multi-objective or optimization problem. What was the optimization we want to do? We wanted to optimize the number of sensors. We wanted to optimize the routing, the placement of the sensors. So we wanted to optimize the energy consumed by the sensors. So there was more than one problem we needed to optimize. So actually we studied some of them together and some of them we studied them separately. So the two that we studied together was the optimization of the energy as well as the routing, the energy due to routing. So we tried to develop a way that optimizes the route. So we have to select the best route for sending data. Why do I say route? Because when we use generally a wireless sensor network, not all of the sensors are connected to the base station. So some of them are connected to the base station and some of them are actually connected to other sensors. So there is many methods to do here. Some of them are what we call centralized, some of them are decentralized, and sometimes we do semi-centralized. So we try to see what will be the best to solve this issue, and we had our optimization equation. The second was we tried to minimize the number of sensors. And this was the work of a master student, actually, a student that was working on her master. She tried to optimize the number of sensors, and she tested with more than one optimization technique. One of them was the genetic algorithm. And I will show even a comparison between the different methods. So this was our optimization problem. We have to maximize the quality of the data that we are obtaining. And this is done by sensor placement. And the second was minimizing the total energy we are going to consume. So the equation, the optimization problem is shown at the right, taking in consideration these constraints. A constraint of the distance, a constraint about the energy we can consume, so we cannot actually have more energy than the initial energy we're starting with. And the last constraint is the number of sensors we have. So here we took one of the examples. This was a 9-story building. And we tried to use this problem and study it to see how can we optimize or apply the optimization problem. So we found that with the number of sensors, the optimization problem you see at the left, it's the quality over the energy. So we are trying actually to have the maximum of this. So we want to have one. If we can have one, it will be best. So we found that if we have the 9 sensors in the 9 floors, for sure, it will give us the best in all of the cases, okay? The second, if we have only 8, we can reach this, we can reach 0.8, the ratio here, okay? This is normalized value, of course. And we found that as much as we go deep, we go less number of sensors, we will reach a point where actually for sure the data that we have is the ratio is very low. It means that we are consuming a lot of energy and we are not getting as much good data as we want. By the way, this could be not because of the data is not good, but it could be because of the energy due to the having the sensors far from each other. They are consuming more energy, okay, to actually send the data. So we had here, this was the second problem I told you about, the second problem, which was of the master student, trying to minimize the number of sensors. We tried 3 methodologies here, the exhaustive search, the genetic algorithm, and the binary search. And we tried on a 5-story building, a 9-story building, and then a 2-bay 9-story building. We had the optimization problem defined, and we had here the requirements for each one. The L here is the requirement we got from the civil engineering, that whenever we are going to calculate the L of S, which is a requirement that we have from them, it should be in a certain range, okay? There is an L minimum, it cannot be less than this. And they gave us some numbers about this. So when we use the 5-story building, actually putting the sensors, we were able, as you can see, to generate 5 mode shapes. So we have in front of us the 5 mode shapes of this 5-story building. The first 5, actually there are more, but we only use the 5 first mode shapes. And you can see that we put the sensors in 5 different floors. And what you can see of the left, that this is the height. And we put a sink, which is in yellow, to the right, okay? And what we had is that we tried to see what will be can we generate 5, which is the mode shape, actually, matrix. And we did this for the 9-story 2-bay. So let me show you a comparison that we had here for the different techniques that had been used. The exclusive search, the genetic algorithm, and the binary search. So we found that the L minimum, as you can see, it has been defined for a value of 20, 40, 60, 80, and 100. And of course, we found that the more sensors you have, for sure, you will have better value, okay? But we found that at the same time that we can have for 9-story building, when it's actually without 2-bay, we can actually use a very little number of sensors. So even 8 sensors was good. But when we are actually using a 2-bay, we found that we have to use a lot of sensors. Okay, so it was a finding. So what did we do? We said, okay, let's see where will be the best placement of these sensors using the different techniques. So what you see in front of you at the right is the placements, and the color inside these boxes is the color that was generated by the different 3 techniques. So for example, the blue one is the exhaustive search. It found that these are the location that we have to place the sensors in. When we use genetic algorithm, there was only these locations that will give us the best values. And when we are using the binary search, it gives us the ones in yellow. Okay, so it was very interesting actually, this study. And this was the comparison based on the LMIN, as you can see at the bottom, and what is the number of sensors that should be used to obtain the requirements that they want. So we found that in each of the type of the buildings, you can see the yellow, the blue, and the red are the different 3 cases we studied. So you can see with the red, actually, we found that we can use only 5 sensors in a 9-story building. So it was very interesting because it's actually dividing the number of sensors by 2. So it's 50% of the sensors. Okay. So let me go to the 3rd point. The 3rd point is it's generally the last point I'm going to present, because the one after is some future work. So we wanted to analyze and improve the reliability of the SHM monitoring system. So we will apply actually 3 things we are going to do. We are going to test and study the impact of the time synchronization error, and does it really have an impact on the mode shape? So we will show that really it has a huge impact on the mode shape. Second, we are going to see if it is feasible to harvest vibration energy from wireless sensor network from the structure that we are monitoring. So it's very interesting, because we will find that there is a requirement. If we satisfy it, yes, we can harvest energy. The last point is that we try to maximize the lifetime in wireless sensor network with and without energy harvesting. So we said, what if I cannot harvest energy? How can I actually maximize the lifetime of the sensor? So the first one about the synchronization error, we studied the case of having a centralized and a semi-centralized. So what you see in front of you here, the one to the left, it's all centralized. It means that we are actually sending the data to the base station, and the base station is the one who's checking all of everything. It's calculating, it's checking the damage, it's doing everything. While in the other, the semi-centralized, what we do is that we have each one of the sensors is partially processing the data. So they are doing some processing on the data before they send it to the base station. So here we can see the effect on the first 3 mode shapes. So you can see that we studied it when they was perfectly synchronized, when there was an imperfectly synchronized in case of centralized, and in case of distributed. So that it was all of the calculation was done on the base on the sensors. So you can see the perfectly synchronized. There is a difference, and when we increase the number of the nodes we have, we will see that there is a difference here in between the perfect and the imperfect. And the problem, and the problem is that with mode shapes that starting from 4, we've seen that it's completely damaged. So it's another mode shape. So we will not be able actually to check the health or monitor the health, since they are completely damaged. The curves or the data that we are using is having problems. It's not reliable, so we cannot use. And we actually published this work in one of the good conferences, WCNC. And here, this shows you another study. We tried to change the frequency, which is the beta TI, based on the sampling frequency. We tried to change and see if we will get something better or no. And we looked at the probability of false detection and the time synchronized and the probability of detection or missing a detection. And you can see that we actually have a problem with the time synchronization error increasing. The probability of detecting or missing a detection or false detection increases really fast. So what we tried to do, we tried to introduce the FFT and see if we do some FFT before sending the data, would it make some difference? We found yes, it will make some difference. So the second curve, for example, the probability of false detection, you can see there is a difference between the first and the second case. And it depends a lot on the number of samples we are going to do, okay, the sampling we are going to use. So the last point was analyzing and improving the availability of the SHM. So now we want to extend the battery life. We want to eliminate the need for human involvement in maintaining the batteries. And we wanted to prove that it is feasible to harvest energy from vibration to power these sensors. So to do it, we had to do something really logic. We had to see how much energy does the sensor require. So I will show you a curve. This is the type of sensor. So this is the algorithm we did, or this is the steps we used. So we had the sensor, we identified the sensor, we built an energy harvesting circuit. We wanted to see if we can store energy. So we used two options. Either we use a battery or use a supercapacitor. So if we use a battery or a supercapacitor, what will be the difference? So after doing this, we developed an energy management scheme that will manage when to connect to the battery and when to start sampling and taking readings. And then this is the sensor node we used. And this is a very specific sensor node. It's the MEMSIC crossbow, which is used a lot in structural health monitoring, actually. These are the modules we use. So you can see this is the sensor. This is the piezoelectric at the bottom left. And we tried to see what will be the readings in the case that we do it in the lab. So we did the same. We took the sensors, we put them in the lab on the shaking table. We did the shaking with frequencies that are actually also given by civil engineer to see if it will generate enough energy or no. And we found that as much as the load resistance increase for sure, what will happen is that the output output power will be really low. So we had really to find a way to see how can we minimize the load resistance. This is the most important finding in this feasibility study, which is the requirements. We found that the energy of an active mode to capture one sample plus the energy of transmitting this sample, okay, it's actually equal to 0.5 milliwatt per second. So if we can have something that give us more than 0.5 milliwatt per second, okay, milliwatt second, then for milliwatt second, then for sure we will be able to get to accommodate the requirement of the sensor. Okay, so what we did is that we seen what was the load of transmitting, what was the active load when the mode is active, when it is sleep mode. So the other thing is that we try to make the sleep mode more frequent. So what happens that you can see during the sleep mode, the load, it's in microwatt, the power consumption in microwatt. So it's really low compared to milliwatt. So this was very important that we can manage this. So the finding at the end says that if we want to manage and we want to have a vibration, a harvesting vibration, we can have readings, okay, up to 0.365% of the duty cycle. So what happens that we can harvest energy in like 1/3 of the time, okay, and we can use the sensor in 2/3. So this is 36.5%. It's 0.365, okay, of the duty cycle. So I think I will show one thing that we really want to work on the future is that we want to accommodate some of the things that we already developed and to have them in real life projects. So as I said at the beginning, not all of the buildings are the same. Some buildings are residential, some buildings are factories, some buildings could be a stadium, it could be a railroad, it could be a bridge. So it's really different. But one of the problems is the installation cost and the running cost of these installations. So it's very difficult to install a monitoring system on all structures in the city or in a country to monitor all of these, especially if this region, for example, let me say in California, there's a lot of earthquakes that happens. So they are building all of their buildings that accommodate a certain code. But what if a certain very high earthquake happens, a very strong earthquake happens, and we don't know if these buildings and these structures are usable? We don't know. How can we do this? This is the challenge we want to do. We want to test buildings and know if these buildings or these structures, bridges, stadiums can accommodate people without having to be tested using a certain civil engineering like panel or something that go and test these buildings. Sometimes it's very difficult. Here, if a hurricane happens, what if we want to test and some of the buildings partially had been damaged? Can we know that all of these buildings are safe to live in after this? This is what we want to see. We want to study. We want to see a method that helps us to see if these buildings are usable after a major disaster or no. And I thank you very much. And if you have any questions, please.
Well, thank you very much, Dr. Elfouly. This was very interesting presentation. And as you mentioned, structural health monitoring certainly is something that's been around for a long time. It actually took me back for a while when I was studying for or doing my master's degree. Happened to be my cousin was doing his Ph.D. at University of Maryland, and he was at that time he was instrumenting very large beams. A project for his PhD was funded by Federal Highway Administration, and ultimately what he was trying to do is detect cracks in large beams.
Yeah.
And of course everything was wired and so on and so forth. So it was exciting, those large beams, and those procedures have been in place. But when I look at your presentation, the amount of advances that has happened in terms of both sensors and communication, in terms of wireless communication and monitoring of those, have really opened up what you can do, and it's really certainly exciting. And it's many other areas as well, as you well know, in terms of
it is challenging.
Aircrafts as well has been a lot of usage. So
yeah.
Anyway, I don't want to talk anymore. Open it up for questions. Please just simply turn on your video if you like, or turn on your microphone and ask questions. See, Dr. Mahajan has his microphone on, so that means he may want to ask a question.
Yeah, I have a couple of questions. First, is vibration the only point of interest from the point of view of structural health? So are those the only, you mentioned 500 micro G.
Yeah.
So that's fine, but do they look at something else?
No, actually it was all vibration. Most of the professors, most of the researchers I found, especially in civil engineering, they work on strain actually. What I've seen is that they put certain sensors but they have to be in certain locations. But mainly our work is on vibrations, yes.
Then I liked your idea of harvesting energy while the vibrations are there, and kind of powering, self-powering kind of sensors.
Yeah, and it's actually very cheap because it will not be like solar. The problem with solar is the solar panels. Maintaining the solar panels and it's the maintenance. Yeah, it's really costly.
Otherwise, but you use about 9 sensors, 8 or 9 sensors.
We used actually up to 30 sensors. This is what we used.
Up to 30, yeah.
They are very expensive, the sensors we used. We used on the bridge only the Raspberry Pi with 4 sensors, because this is cheap. But the sensors that we used in the building, the 9-story building and the 2-bay, we used up to 30 sensors. The problem is that every 6 sensors is $5,000. So it was really very expensive to use these type of sensors. And this gave us actually the motivation to work on the Raspberry Pi and use very cheap, because the Raspberry Pi with the 4 sensors will cost around $50. So it's really cheap.
Of course, it's always a good idea to use as less sensors as possible.
Yes.
But if you want reliability, it's better to have as many sensors as possible and redundancy.
Yeah.
So powering those sensors, you may know, Vanessa and we have this wireless power transfer.
Yeah.
You can wirelessly power transfer and charge the battery of the sensor or whatever is there.
Yeah, I've seen even some are doing it using now drones. They are charging sometimes these sensors using drones, by the way. They pass certain drones over an area with a very strong radio signal, an electromagnetic wave, I think, because this is not my field actually, but they actually charge the sensors on the ground using this. And sometimes I think it's very good. They use it in forests, they use it in rural areas.
Is that microwave power transfer?
I think it's microwave, yeah.
It's RF, actually.
Yeah, it's microwave.
Radio frequency. Yeah. Okay, so the thing that you mentioned about mobile crowd sensing, I could not quite understand what exact applications it can have.
Actually, I think it has a lot of applications. If you look at now, all mobile phones that we have sensors embedded in them. All of them. They have actually the accelerometers, they have gyroscopes, they have all the type of sensors we need are in a mobile phone. But no one is using these sensors actually. We are only using them to check if we are moving or no.
So are you suggesting that you you can use mobile phones to
Yes.
monitor structures?
Yes.
Okay.
And it is feasible, by the way. I will tell you, we tried on this bridge. This bridge is in Memorial University in Canada. And you can see the bridge is not a very short bridge, actually, but it's a pedestrian bridge. And they had a student who worked on his master there, because one of the PIs of the project I worked on was in Memorial University at that time. He left Memorial, but he was at that time there. So what we did is that we studied if it is possible to put the mobile phone in this bridge and check if it will give us readings or no. Okay. And we tried that. He tried it when no one was moving on the bridge, when people were moving on the bridge, when he was moving on the bridge, and we found that it's possible. So actually we can detect if we can actually get the natural frequencies of the bridge.
Very nice. Very nice. Yeah.
So it was really interesting. So we proved actually this.
I'm sure you'll be able to work with some civil engineering faculty.
Yeah, of course. Of course. Actually, I'm working with a mechanical engineer faculty now on working on something like this, and I think he's really very good. I think we will be able to write something about this. And actually, I talked to Dr. Mutavelli, and he told me to contact you about it.
In Oak Ridge, they have, I'm not sure if it's a division, but a program for sure related to buildings. And
yeah, but this is not only buildings. This can be for bridges. So I think having
no, I was talking from the funding and collaboration point. I'm sorry. Yeah, go ahead. Go ahead.
What I mean, if we can really have someone from the DOT, I think it will be really interesting to show them what we can do with this.
Okay, I'll keep quiet. Let others
No, please go ahead.
Questions.
Please go ahead.
I mean, let's see if if there are no other questions. Yes, you can certainly continue. I know that some other faculty have worked in this area. I think maybe Dr. Anton. Yes, he's
yeah.
Hey, video to ask.
I just have a quick question. Great presentation and interesting work. So from I guess the circuit side of things, you've used some commercial off-the-shelf sensor nodes, wireless sensor nodes, and some energy harvesting circuit chips that are commercially available. Have you done any development of customized or optimized circuits for either the energy harvesting part or for the sensing part?
No. I think it will be great to do this, but actually in the project, it was not one of the goals. But if we had someone really in this field, it would have been great, because if we can minimize the energy consumed by the board, for sure it will live more. So this will be interesting, of course. Yeah, for sure.
Yeah, I know some commercial ones are probably, obviously they're not optimized, so they work, but they're not going to be the most efficient solutions.
Yeah.
So we can catch up later, I think maybe perhaps offline, but I would be curious to see what because you were collaborating with some MEs, some civils. So, what is your expertise, I guess, within all this, kind of what area did you specialize?
It's in the microcontroller part.
The microcontroller. Okay.
Yeah.
Okay. So microcontroller that can talk.
Plus the wireless communication part.
Okay.
The protocol itself, because we actually tried to do some routing protocol. So it was in the protocol plus the microcontroller part.
Okay, and some of that was the synchronization errors that you were talking about for estimating mode shapes and things.
Yeah.
Okay, great. Thank you. I just wanted to make sure I kind of knew what your expertise area was. So thank you.
Actually, really, I hope that we can build a board with a sensor that can do this. I think this will be the best.
Yeah, yeah. I've been
Actually
looking.
reveal everything. Yeah.
I've been looking for folks on the electrical engineering side that would be able to build energy harvesting circuitry and SHM circuitry. So I think this is really something we should try to identify, because I think then you can get some advances, you know, and try some new things. So anyway,
what's
great.
interesting here, I think, if you're really interested in this, what's really nice is that we didn't think about buildings or bridges that can generate enough energy, using or vibrating to generate enough energy to actually to work. But we found that bridges actually vibrate a lot, and buildings vibrate. They are moving all of the time. So is it why we are losing all of this energy without using it? So this was the point of it's there. The vibration is happening. So why not actually harvest this energy? Why try to harvest energy from the sun while you are actually having energy generated for you from, and you are not using it? And this is why we did the feasibility study, to see if it is possible or no. And we found it is possible, but you cannot for sure make the sensor work 100% of the time. It's impossible. Otherwise, the battery will be depleted really fast. So we found that there are certain restrictions.
Great. Thank you.
Thank you.
Thank you for that question, and thank you for your questions, Dr. Mahajan. Any other questions? Well, if not, we can end right on time. We started a couple of minutes late just to let people join in, but 5:30, and we can end our seminar, and thank Dr. Elfouly for a very interesting presentation, and thank you all for attending. Next seminar will be by Dr. Rory Roberts, and it will be next Tuesday, October 27th, same time. And his talk will be in design and optimization of multidisciplinary dynamic systems. Thank you again, and have a great day.